In section 2.5, we're going to be talking about measures of position. So that's going to be like, where does a specific data value fall in relation to the entire distribution of data? So the first thing we're going to talk about is quartiles. What quartiles do is they divide an ordered data set into 4 equal. So we have to start out by putting our data in order, and then we will be able to put it into 4 equal parts. So the quartiles are called Q1, Q2, and Q3. So Q1 is the first quartile. And what's going on there is that 25% of your data values fall on or below this value. Then we have Q2, which is the second quartile. It has another name that I'll tell you in a moment. And 50% of data fall on or below this value. So thinking back to what's going on with our data, what would the data value be called that's right in the middle when our data is in order? So half of them are above and half of them are below. Well, what we have called that in the past is the median. So Q2 is also called the median. Then Q3 is the third quartile. And 75% of data fall on or below this value. So let's look at an example of calculating our quartiles for a data set. Yeah, that's super crooked. The number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed. Find the first, second, and third quartiles of the data set. And what do you observe? So we're going to use this same data for several other types of measurements and explanations and procedures that we want to do. So keep it handy. In order for us to figure out Q1, Q2, and Q3, we're going to have to first put our data in order. So that's our first step. So we want to go from smallest to largest. We barely made that work. Then to figure out where the quartiles are, we're going to start by finding the median. So the median, remember, is when half of the data is below and half of the data is above. So once your data is in order, you can just kind of count in to the middle, making sure that half is above and half is below. So this right here, that middle data value would be the median, or Q2. And then to figure out where Q1 and Q3 are, Q1 is going to be the median of the lower half, not including Q2 or the median. So what we do is we ignore from the median up. So all of that data doesn't count right now. And then we're finding the median of just these values. So we go to the middle, and this right here would be Q1. Then to find Q3, Q3 is going to be the median of the upper half of the data. Again, not including Q2. So now we're going to ignore all of these numbers and find the median of just this half of the data. So we count in, and that would be Q3. So our Q1 is going to be 9. Q2 is 16. And Q3 is 33. So how do we then interpret that? What we would say here, Q1 equals 9, we would say that 25% of the countries have 9 nuclear power plants. I guess 9 or fewer nuclear power plants. And then since Q1 is 16, we would say that 50% of the countries have 16 or fewer nuclear power plants. And then Q3 is 33, which means that 75% of the countries have 33 or fewer nuclear power plants. Now remember that your graphing calculator will be able to help you find Q1, the median, and Q3. We had mentioned that under one variable, statistics. So the graphing calculator can give you Q1, median, and Q3. And that is under the menu Stat, and then arrow over to Calculate, and then choose option number 1, variable statistics. If I'm asking you to do this on a test or when you're practicing on my math lab, you should do some of these at least by hand so that you know how to do them. Now we can use Q1, Q2, and Q3 to create a box and whisker plot. And you'll probably remember doing that in the past. So I'm going to give you the instructions on how to make a box and whisker plot, and then we'll practice using that nuclear power plant data. So box and whisker plot. The first thing you're going to want to do is find something that we call the 5-number summary. The 5-number summary includes, it's going to be shocking, 5 numbers. The first number is the minimum value in the data set. The second value is going to be Q1. The third value will be the median, also called Q2. Fourth value is Q3. And the fifth value is the maximum value of the data set. Then we are going to create a horizontal number line. And this needs to be drawn to scale. So I can't just put the specific numbers that I want on there. And we're going to plot the 5 numbers that we just found above the axis. I think we'll go ahead and get those steps done, and then we'll come back and write in steps 3 and 4. So we're still going to use that power plant example that we were just talking about. So our 5 numbers, the minimum number that we had would have been the first one on our ordered data list, which was 6. Q1 was 9. Q2 was 16. Q3 was 33. And our maximum number was 104. So when you make your horizontal axis, we have to go all the way from 6 to 104, and it has to be done to scale. So in other words, if I'm like going by tens, all my tens have to be the same size, and I can't skip any numbers along the way. So let's say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. That's not going to work. I'm going to have to add another piece of paper on here. Okay, I had to put an extra little piece of paper under here to get all the way out to 104. So, yikes. Hopefully you will do a better job of making your scale than I did. Then what I'm going to do is put the 5 numbers above the number line. So I'm just going to put dots up above for each of those values. So my minimum was 6, that's 5, so we'll go up to 6. And then 9, 16, 33, and 104 all the way out here. Okay, after I have those numbers plotted above my axis, I am going to draw the box part of the box and whiskers from Q1 to Q3. And then inside the box, I'm going to draw a vertical line. So from Q1 to Q3, that's from 9 here to Q3, 33. I'm going to draw a box. And then I'm going to draw a vertical line inside the box at Q2. So that's the box part of the box and whiskers. And then we are going to draw whiskers from the box to the min and max. So the whisker part goes from the box to the min, and then from the box to the max. So I may have to Zoom out a bit. So here is my box and whisker plot of the nuclear power plant data. Now let's look at some observations that happen when we have a box and whisker plot. If you look at the box, remember that these values were found by splitting our data set into quarters. So we have 25% of our data here, 25% here, 25% here, and 25% here. So what you can kind of tell is that the bottom 25% of the data is really clustered together. The top 25% of the data is really spread apart. What we've got going on in the box is that 50% of the data is in the box. So half of my data values are represented in this box. And then 25% of the data is in each of the whiskers. And then what you can say about this is that when we have a very long whisker, that means there might be an outlier. So what we're going to do is use something called IQR to check for outliers. IQR is the abbreviation, or I guess the acronym, for interquartile range. So IQR, interquartile range. We're going to use interquartile range to determine if there's an outlier because it is a measure of variation or spread of data. And what it does is it tells you the range of the middle half of the data. So interquartile range is the range of the middle half, or interquartile, middle half, 50% of the data. To find IQR, you're going to take Q3 and subtract Q1. And then the reason that we're finding this is to be able to identify outliers. So to identify outliers using IQR, first, of course, you're going to have to find Q1 and Q3. Then second, you're going to find IQR, which is going to be Q3 minus Q1. Okay, here's where the formulas come in. So we're going to take Q1 and subtract 1.5 times IQR. And then we're going to calculate Q3 plus 1.5 times IQR. And then the outliers are any value below this number or above this number. So let's look back at our power plants and figure out if we have any outliers. So from our power plants, we know that Q1 was 9, and Q3 was 33. We've already figured those out. So we want to compute IQR, which is Q3 minus Q1, so 33 minus 9, which is 24. And then we've got to do that Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. So we'll take 9 minus 1.5 times 24, which will be 9 minus 36, and that gives me negative 27. So that tells me that any number or any data value below negative 27 would be an outlier. Our lowest data value was 6, so that's not an outlier. Then we'll take Q3, which is 33, plus 1.5 times IQR, which was 24. So that's 33 plus 36, which is 69. And then that means that any number above 69 would be an outlier. So if we look back at our data set where it was all put in order, we only have one number that's above 69. So we could then identify 104 as an outlier. Another way to measure the position of a data value besides using quartiles is to use deciles. So deciles, what they do is divide ordered data sets into 10 equal parts. So instead of using Q1, Q2, and Q3, we're going to use D1 for decile 1, decile 2, decile 3, all the way up until decile 9. So if we wanted to go to the middle half of our data, like we did with the median would be the same thing as D5. And remember that in quartiles, Q2 was the median, so Q2 is the same as D5 when you work with deciles. Another way to measure position is using percentiles. Percentiles are going to divide the ordered data set into 100 equal parts. So you've heard percentiles used most frequently probably in education, like if you look at your SAT scores or ACT scores or state assessments or MAP scores, they'll tell you you're in the 92nd percentile. And so what that means is that 92% of the data values or 92% of the people who took that test scored lower than you did. So percentiles are often used in education. And then if you know anyone who has like a baby, when they go to the doctor's office, then they'll be like, oh, my baby's in the 75th percentile for height and the 84th percentile for weight. So we use that often in education and in health-related fields. So percentiles, we're going to use the letter P. So P1, P2, P3, all the way up until the 99th percentile, P99. So the median with percentiles, median would be P50, and that would be equal to D5, which would also be equal to Q2. So with percentiles, though, we can split it even further. So like P25 would be the same as Q1. We can also equate percentiles to deciles. So like D1 would be the same thing as P10. So you can kind of go back and forth between percentiles and other measures. So let's look at, speaking of SAT scores, let's look at this little SAT scores example. Do you recognize what kind of graph this is? That starts at 0 and works its way up to the 100 mark. Remember, that is showing cumulative frequency. That kind of graph is an ogive. So this is an ogive that represents cumulative frequency distribution for SAT scores of college-bound students in a recent year. They want to know what score represents the 62nd percentile. So they've kind of given you a helpful hint here that we would look at the 62nd percentile. So 62nd percentile is right here. So we would follow that over to our ogive, and then we would follow that down to figure out our score, which would be about a 1600. We can also read this the other direction. So what if I wanted to know what percentile would correspond to a score of 1200? So this time I'm going to start at 1200 and work my way up onto the ogive and then over to the percentile. And depending on how accurate I am, so this is like 15 is halfway between. So I would say maybe the 17th percentile. I'm just estimating because I don't have a very accurate graph going on there. Now, if you have the data for a data set, you can actually figure out the accurate percentile. So we're going to look at doing that. If you have an ordered data set, data list, you can find the percentile that corresponds to a specific data value X. So to do that, the percentile of X is equal to, we have to count the number of data values below X and then divide that by the total number of entries or the sample size. And whoop, spelled that wrong. Entries. There we go. And then we're going to multiply that by 100 to make it into a percent. So we have an example that we're going to do here. For this data set, we're going to find the percentile that corresponds to $30,000. So our numbers are in order already. So to find our percentile, we're going to need to count the number of data values that are below X. In this case, X is 30 because it corresponds to $30,000. So I find my 30 and I count the number of data values below it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to take 9 divided by the number of data sets. So there were number of data values. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 9 divided by 25 and then times 100, which is going to give me 36%. So what that tells me is 36% of tuition costs are below $30,000. We're going to talk about another way to measure position using the mean and standard deviation. So if you know the mean and the standard deviation for your data set, then you can measure position using z-scores, which are also called standard scores, for data that is approximately bell-shaped. So your data has to be approximately bell-shaped in order to use z-scores. And the reason for that is because what a z-score does is it takes that idea of having the mean plus 1 standard deviation and the mean plus 2 standard deviations and the mean plus 3 standard deviations and converts the number of standard deviations into the thing called a z-score. So on a scale from 0, and then we have a z-score of plus 1, a z-score of plus 2, a z-score of plus 3, and then minus 1, minus 2, minus 3. A z-score of 0 would be exactly at the mean. So the mean has a z-score of 0. If you are 1 standard deviation above the mean, then your z-score is positive 1. If you are 1 standard deviation below the mean, then your z-score is negative 1. So when we look at z-scores and we think about them in terms of standard deviations, remember that if we were within 2 standard deviations of the mean, then we would be considered usual scores. Because if we were 2 standard deviations or more above the mean, so in between 2 and 3 would be where our unusual data values are. And then if we were 3 or more standard deviations above the mean, we would be considered to have a very unusual data value. So our normal or usual scores are going to be between positive 2 and negative 2 standard deviations from the mean. So our usual scores would be between the z-score of negative 2 and positive 2. Then unusual would be between negative 2 and negative 3, or, I cannot spell, 2 and 3. And then very unusual would be 3 or more standard deviations away from the mean, which means the z-score is higher than 3 or lower than negative 3. So let's get a formula for z-scores. Well, all of these are z-scores. So z equals 1, z equals 2, z equals 3. The way that we calculate a z-score, it's very easy. The z-score is equal to the data value minus the mean divided by the standard deviation. So using symbols, if you have a population, it would be x minus mu divided by sigma. If you had a sample, it would be x minus x bar divided by s. So any z-score that has a positive value means that the data value is above the mean. Any z-score that has a negative value means that the data value is below the mean. And if the z-score equals 0, the data value is equal to the mean. So let's practice finding z-scores and then comparing z-scores. So finding z-scores will be first. The mean speed of vehicles along the stretch of a highway is 56 miles per hour with a standard deviation of 4 miles per hour. You measure the speeds of 3 cars traveling along this stretch of highway at 62 miles per hour, 47 miles per hour, and 56 miles per hour. Find the z-score that corresponds to each speed. So we're going to find 3 z-scores. One for 62 miles per hour, one for 47 miles per hour, and one for 56 miles per hour. So the formula for z-scores is to take the data value minus the mean, divide by standard deviation. So for 62 miles per hour, z would equal the data value, which is 62, minus the mean, which they said was 56, divided by the standard deviation, which was 4. So our z-score would be 62 minus 56, divided by 4, which is 1.5. So what that tells me is that this data value of 62 miles per hour is 1.5 standard deviations above the mean. For 47 miles per hour, we're going to take data value minus the mean, divide by standard deviation. So the data value is 47, the mean is still 56, and the standard deviation is still 4. 47 minus 56 divided by 4 is negative 2.25. So that tells me that 47 miles per hour is 2.25 standard deviations below the mean. So if I compared these two, the value of 2.25 tells me that this data value is further away than this data value because its z-score has a higher magnitude. The sign of the z-score tells me that it's below the mean versus this one being above the mean. For 56 miles per hour, I'm going to take my data value of 56 minus the mean of 56, divide by the standard deviation of 4, which gives me a z-score of 0. And that tells me that this data value is at the mean, which we could have said just by reading it. But we went ahead and calculated it. Now let's compare z-scores for different sets of data. So we're going to look at men's heights versus women's heights. And we're going to figure out the z-score for a 6-foot-tall man and a 6-foot-tall woman. So this is population data. You can tell because they use those Greek symbols. So for men's heights, for men, at a z-score of 6 feet, which would be 72 inches, the z-score would be, we take the data value, 72, minus the mean, which was 69.9, and divide by the standard deviation, which was 3.0. So 72 minus 69.9, and then divide by 3. That's a z-score of 0.7. For women, the data value is also 6 feet, which is still 72 inches. So our z-score for the women would be the data value of 72 minus the mean, which is 64.3, and then divide by the standard deviation of 2.6. Which is going to be 2.0. 2.96. So with a z-score of 0.7, 0.7 on our scale is above the mean, but it's in the range of usual scores. So for the men, a 6-foot man is what we would consider a usual data value. So a 6-foot man would be a usual height. But if we look at the 6-foot tall woman, a z-score of 2.96 puts that person up here, which is in the unusual range, almost in very unusual. So we would say that a 6-foot tall woman would be an unusual data value.